Okay, we're live. So again, if you don't want to be on the video, don't talk. So uh, here's the visual for going up and going down, and so you'll see that on elevators, and we're going to implement going down triangles. They're a little bit different than what we looked at in the example because the example had one side vertical, one of the edges was vertical, and here both are at an angle. Actually, like I said earlier, the vertical takes extra work because you have to check to see if you're dividing by 0 when you do a slope. Okay, so again, the goal is to apply the scanline algorithm to going down triangles. There's a file called project1b.cxx. It has the triangles defined in it. It's due on Monday. This may be a little fast for this deadline. I'm going to lecture on Tuesday, but then I'm going to Houston to teach that tutorial. And so I would really want to be here and support you guys and hold office hours and be meeting with folks. So I'm trying to incent everybody to get going on this over the weekend and to meet with me Sunday and Monday. If you can't get it done by Monday, it is a little fast for this deadline, and that's why there's an extra late pass. So you now have 3 late passes, specifically so you can have an extension on this project. But I'm hoping that you'll meet me halfway and try it over the weekend, and I can help you with your questions, and then you'll be able to essentially earn an extra late pass by doing so. Nara, can you not shuffle your bags? So good. As I already said, Project 1C, you're going to implement the scanline algorithm for arbitrary triangles, so you need to plan ahead. Let's just look at the prompt real quick. So here's Project 1B. I did actually implement and post 1C this morning, and so if you want to look ahead to 1C, you can. There's a PDF, and it's got my tips, and here is a beginning program. Whoops, that's 1A. Sorry, here's the PDF, and that's my tips. And then here's the beginning program.
That's 1A.
I could say, oh, I'm right and all you guys are wrong, but I mean, it's caught on film, right? That's a very losing argument.
Right-click, open a new tab is useful.
I don't like that. The suggestion was to do a right-click and open a new tab. I feel really comfy with VI, and I just like to navigate files in VI. So one of the things you'll see, and this will actually be what I'll talk about for the remainder of our time, is floating point precision is an issue. And all of these need to be pixel correct. There's a differencer program. The right image is posted. You need to run differencer and have it say exactly the same. If you don't, you will get less than half credit. I don't, something that's close, I really don't even want to score those, right? I would rather have it be right and late than on time and not working, especially because this is a building project and you have to use it for the next 5 weeks. And so the problem that we run into is that on different computers, the calculations, or sometimes it's computer and how the calculations are carried out, sometimes it's your implementation, which is conceptually correct, is correct, but it's different in terms of how I implemented it, and then we end up with slight differences in terms of where we think the intersections are. And so the brave fallen people who took the first version of this class, and I debugged this issue. You guys are the 4th cohort to take this. We're able to get everyone to get the same image, but you have to use these ceiling and floor functions at just the right spots, right where they are in the scanline function, where I have them in the pseudocode. So make sure you're using my ceiling 441 and floor 441 in those solved problems. Okay? So this is the same thing that's in 1A. There's something to make a new image. There's something to write an image. I defined a triangle struct, or triangle class for you. And so there's an X and Y vertices for each. And there's a color. So this is a single color for the entire triangle, right? Let me make that slightly bigger. It's perfectly big on my screen, but it may not be big enough in the back. And so, of course, there's 3 vertices in a triangle, but there's one color, and this is RGB. There's also a screen, and so the screen has, a buffer and a width and a height. And so in this case, this program will actually generate the triangles for you. So there's a routine that generates a vector of triangles. In 1C, there's actually going to be a data file that goes with it, and the program will read from the data file. You'll still call get triangles. You'll still get a vector of triangles, but it won't be something generated by my own loop. It'll be something that's read from a file. So then in the main program, I make an image. I instantiate the screen. I set the data member for the buffer for you, and then it says your code goes here to deposit triangles. I should say deposit the colors of triangles into pixels using the scanline algorithm. Okay? So that's what's in the code. And then that's the image you're going to make. So these are all going down triangles. Now they don't look quite like what you see in an elevator because this bottom vertex is, in some of these rows is pretty close to the midway between the left and right top vertices, but in some cases they're kind of far off to the right. But you're going to, for each of these triangles, apply the scanline algorithm and deposit the colors from those triangles. Okay? Okay, so I'm going to keep lecturing. I'm going to stop the video unless there's questions. Okay, I'm going to stop the video. I'm going to lecture on why we have floating point differences.